Hello everyone, this is Aswini Pandiyan, and in this video I'm going to explain about different types of lasers.
So in this video we are going to see about types of lasers. So there are three types of lasers and let's see about it. So before knowing about the types of lasers, let's first see the components of a laser. So there are three components. First one is active medium, which is also known as gain medium, and the second one is pumping energy source, and the third one is resonance cavity, which is also known as optical resonators. So over here in the image, the region D is the resonance cavity. On the both sides of the resonance cavity, it has one side as an highly reflective end mirror and the other side as a partially transmissive output coupler. And inside it there is an active medium which is filled of atoms and a pump. So active medium, it is a material in which the laser action takes place. Active medium contain a collection of atoms that can be in an excited state using external sources like radiation or through electrical or chemical ways. These atoms can be excited to a higher energy level. The atoms later relax to a metastable state. As a result, population inversion can be achieved in this medium. The active medium may be solid crystals such as ruby or NdR, or liquid dyes or gases like CO2 or helium, neon, or even semiconductors are used. Pumping energy source. Energy source pumps the active centers from ground state to excited state to achieve population inversion. There can be three types of pumping sources. One is optical pumping, then it's electrical pumping and chemical pumping. These types depend on the nature of the active medium. In solid state, laser optical pumping is used, and in gas, laser electrical pumping is used. So the resonant cavity, which is also known as optical resonator. In simple words, it consists of two parallel mirrors placed around the gain medium. Among the two mirrors, one is highly reflective, like 100% reflective, and the other is partially transmissive, like 99% reflective. Light generated in the medium by spontaneous emission is reflected by the mirrors back into the medium, where it is amplified by stimulated emission. The light may reflect from the mirrors and thus pass through the gain medium hundreds of times before exiting the cavity. The design and alignment of the mirrors with respect to the medium is crucial for determining the exact operating wavelength and other attributes of the laser system. So let's now see about helium neon laser. The helium neon lasers as an active medium which consists of two gases which do not interact to form a molecule. Therefore, the helium neon laser is one type of atomic gas laser. So this is the construction of laser. Here we can see a gas envelope, and both the side of gas envelope we have one side cathode and the other side anode. The cathode side as the output coupler and the anode side as a high reflector. And inside the glass envelope we can see a laser bore tube. The tube where the laser action takes place consists of a glass envelope with a narrow capillary tube through the center. The capillary tube is designed to direct the electrical discharge through its small bore to produce very high current densities in the gas. The output coupler and the eye reflective mirror are located at the opposite ends of the plasma tube. To make laser tubes more economical and durable, manufacturers often attach the mirrors directly to the ends of the capillary tube. The output coupler and the eye reflective mirror are located at the opposite ends of the plasma tube. The plasma tube has a large cylindrical metallic cathode and a small metallic anode. The current is directed from cathode to anode. So in that figure, we saw a gas reservoir which provides a supply of extra gas. This reservoir helps to maintain a uniform pressure over a long period of time and provides extra gas to replace any gas that may escape through the tube or through the seals where the loads pass through the gas envelope. Usually all helium neon plasma tubes have a gas reservoir. In helium neon lasers, active medium is low pressure gas mixture of helium and neon gas which is contained in the plasma tube. The ratio of He to neon within the tube vary from 5:1 to 20:1. Usually this ratio average 8:1 which is considered. So the function of a He neon laser. In helium neon laser, the light is produced by atomic transition within the neon atom. The helium does not directly produce laser light, but it acts as a buffer gas, the purpose of which is to assist the atoms of the other gas to produce lasing action. When energy from the pumping source is applied to helium neon gas mixture, then some of the energy is absorbed by the helium atoms. In other words, we can say that helium atoms achieve an excited state. Now when the helium atoms move within the laser tube, they collide with the neon atoms. At each collision, some of the energy within the helium atom is transferred to the neon atom and so raising it to an excited metastable state. When a sufficient number of neon atoms reach to its state, then population inversion occurs and hence the lasing takes place. So here we can see the diagram of it. So when E3 and E5 are the metastable states. So when there is pumping source, the atoms from the E1 state moves to the E5 states of the helium, E5 or E3, mostly it will move to metastable state, and then the collision occurs between the helium and neon, and after gaining energy, the neon atoms further move to excited metastable states. Here the upward transmission show the absorption of energy from the pumping source of helium atom, while downward transition shows the emission of energy or light or lasing present in the neon atom only. So here we can see the collision of the helium and the neon atom. So in that diagram, we saw 3 downward energy transition from neon that produce lasing. If transition occur at a relatively small energy step from E5 to E4, then low energy infrared photon is released with a wavelength of 3.391 microns. If transition occur at E5 to E2, which is a much larger energy step than the before one, then it produces short wavelength, more energetic photon at 632.8 nanometer. This gives the red light, which is the most desirable for helium neon laser application. So E3 to E2, then it produces a laser output at 1.152 microns in infrared portion of the spectrum. In all helium neon lasers, the feedback mechanism consists of pair of coated mirrors. The coating is usually reflecting mirror and 95% to 99% of the light at output coupler. The reflection at the output mirror must be higher if the active medium is short in length because the gain of the active medium is low. If the active medium is longer, more gain is produced and the larger percentage of the beam can be provided as an output. Therefore, in the helium neon laser with longer active medium, the reflectivity of the output coupler can be less. So let's see about the characteristics of an helium neon laser. The helium neon laser is a relatively low power device with an output in the visible red portion of the spectrum. The most common wavelength produced by helium neon laser is 632.8 nanometer. Although two lower power like 1.152 micrometer and 3.391 micrometer. Infrared wavelengths can be produced if desired. Majority of helium neon lasers generate less than 10 milliwatt of power, but some can be obtained commercially with up to 50 milliwatt of power. For helium neon lasers, the typical laser tube is from 10 to 100 centimeter in length, and the lifetime of such a tube can be as high as 20,000 hours. So applications of helium neon laser, they are produced in large quantities from many years. Many schools, colleges, universities use this type of laser in their science programs and experiments. Helium neon lasers are used in supermarket checkout counters to read barcodes and QR codes. The helium neon laser also used by newspaper for reproducing transmitted photographs. Helium neon lasers can be used as an alignment tool. It is also used in guns for targeting. So disadvantages of helium neon laser. It is relatively lower power device, means its output power is really low. Helium neon laser is a low gain system or a device. To obtain single wavelength laser light, the other two wavelengths of laser need suppression, which is done by many techniques and devices. So it requires extra technical skill and increases the cost also. High voltage requirement can be considered its disadvantage. Escaping of gas from laser plasma tube is also its disadvantage. So suppressing unwanted wavelengths in HE neon laser. The helium neon laser produces three different wavelengths that are 1.152 micrometer, 3.391 micrometer and 632.8 nanometer. At the first two, the infrared photons are released, while at the third one, more energetic photon of red light are released, because in spectrum at 632.8 approximately red color occurs. For helium neon laser, most application, the red output is most desired, therefore it is necessary to suppress the infrared wavelengths and prevent them from releasing so that the energy directs into the desired output. In small helium neon laser, it is normally done with a proper coating on the feedback mirrors. If they are coated for high reflectance at 632.8 nanometers, then they will not reflect a high percentage of the infrared wavelengths. This causes the desired wavelength to have a low loss and the undecided wavelength to have a high loss, which reduces the possibility in the infrared wavelengths lasing and enhance the lasing at 632.8 nanometer. For high power HE neon lasers, the mirror coating cannot totally suppress the infrared wavelength. Therefore, in these lasers, the magnet is placed near the plasma tube, which provides an additional suppression effect on the infrared wavelength. If these two suppression techniques are not enough to prevent infrared lasing, then an infrared filter can be used between the laser mirrors to absorb the unwanted wavelengths. So now let's see about the CO2 laser. So the first image shows a symmetric CO2 stretch. The second one shows a bend where the two oxygen molecules move in same direction, whereas the carbon moves in different direction. And the third one is an asymmetric CO stretch where none of the three move in same direction. They move in very weird direction, like the O oxygen atoms move in one way, and the carbon moves in their opposite way. So these are called as asymmetric. So these are the vibrational modes of CO2. The CO2 stands for carbon dioxide. In CO2 laser, the laser light takes place within the molecules of carbon dioxide rather than within the atoms of a pure gas. Therefore, CO2 gas laser is considered the type of molecular gas laser. Importantly, note that CO2 lasers use carbon dioxide as well as helium and nitrogen as its active medium. So here it uses
carbon dioxide as well as helium and also nitrogen. So the characteristics of CO2 lasers. CO2 laser produces a far infrared beam at 10.6 microns. It can also operate with an output of 9.6 microns, but this output is not much common. The beam divergence of the CO2 gas laser ranges from 1 to 10 milliradians. The beam width varies from 3 millimeter for low power lasers up to 100 millimeter for high powered lasers. The CO2 laser can be operated in either CW or pulse mode commonly. The continuous wave mode is known as the CW mode. The continuous wave power output can range from few watts to over 15,000 watts. In pulsed mode, peak power output can be in the millions of watts. The construction of a CO2 gas laser. The CO2 gas laser can be constructed in a number of different configurations. In each configuration, there is a specific manner in which the gases flow in the tube. So 5 important configurations of CO2 laser construction are sealed tube design, coaxial flow design, fast axial flow design, transverse flow design, TA design. So this is a sealed tube design. In this design, the gas is sealed within the glass tube. This laser configuration can be pumped either with DC or RF excitation method. So here we can see the image of it, and the gas is sealed inside the glass tube. Here the gases are He, neon and CO2, and we have RF power supply. So if the DC excitation is used with the sealed tube CO2 laser, then it is much like constructed as He neon gas laser. However, it is necessary to have an elaborate cooling system with the laser. If the radio frequency, the RF excitation, is used with sealed tube CO2 laser, then construction can be shown as the above. A figure shows that pumping power is provided and RF power supply. The energy is coupled to the laser using a matching transformer designed for maximum power transfer. The output from RF supply is coupled to a number of electrodes that are kept around the laser tube. The RF energy is absorbed with very little temperature rise. So now let's see about the transverse flow design. So here we can see segmented anodes, we can see heat exchanger, gas flow direction, blower. Here the tangential blower circulates low pressure CO2 gas around the inside of the laser tube. Current flow through the tube is perpendicular to the movement of the gas. So we can see that the current flow through the tube is like perpendicular to the movement of the gas. The optical cavity is perpendicular to both gas and current flow, which means that they are mutually perpendicular. When the gas moving at high speed flows around the inside of the tube, then it passes through the heat exchanger. When the gas moving at high speed flows around the inside of the tube, then it passes through the heat exchanger. This efficient method of cooling permits this type of laser to achieve higher power per unit length of the gas. The disadvantage of transverse flow design is a short and thick optical cavity. TEA design. The TEA stands for transverse excitation at atmospheric pressure. This design is considered the variation of the transverse flow design. With this design, the gas that flows around the inside of the tube is maintained at near atmospheric pressure. This high density gas flow allows extremely high power outputs. However, it is very difficult to maintain ionization of the gas when the gas is at high pressure. Generally, voltages required to maintain this type of operation are extremely high. That is why the TEA design laser can only be operated in pulsed mode. The beam diameter of this type of laser varies from 5 to 10 millimeter. So now let's see about the function of CO2 laser. The CO2 gas laser uses a mixture of helium, nitrogen and carbon dioxide as the active medium. In this mixture, the helium and nitrogen work with the CO2 to produce the desired lasing effect. Here the nitrogen gas acts as buffer gas just like the helium did in H-neon laser. The nitrogen gas absorbs the pumping energy from the current flow in the gas and transfers the energy through collisions to the CO2 molecule. Now when the CO2 molecule drops from an excited level to another level, then the lasing occurs. So here we can see the diagram of it. There's a diagram for symmetric stretch, for bend and asymmetric stretch. So during the process, the lower lasing level must remain with low population. Therefore, the molecule must be removed from the lower lasing level as soon as it has emitted its photon. It is done by cooling the glass, but most cooling system cannot cool the gas quick enough to keep the lower lasing level depopulator. So the helium gas is used in CO2 laser. So when the helium gas enters the process, it removes energy from the CO2 molecule by atomic collision, and so reducing the molecule to the lower energy states. CO2 lasers, the active medium is not only CO2 gas but also the nitrogen and helium exist there too. Here nitrogen gas acts as a buffer gas. Nitrogen gas absorbs the pumping energy from current flow in the gas and transfers this energy through collision to CO2 molecules. So the CO2 molecules reach to the excited metastable state. When they reach to metastable state and drops from this excited level, then lasing occurs. In this way, buffer gas is needed in CO2 gas laser. So we'll see about the application of CO2 lasers. And this is one of the most efficient and useful gas laser discovered up to now. CO2 gas laser can be used in industry, usually for welding and cutting purposes. It is used as surgical tool in operating room. In both energy and weapon research, CO2 lasers can be used. So let's see about the advantages of CO2 laser. In CO2 laser, high power levels are obtained, ranges from few watts to 15,000 watts. The efficiency of the CO2 gas lasers, that is 10% or higher, is better than helium, neon and argon lasers. CO2 lasers have become the workhorse of the material processing industry because of their low cost. In many configurations, the CO2 gas lasers are available. In some cases, its divergence is small, but it's not true always. Pulsed output can be obtained from TEA CO2 lasers, making them more efficient. Lifetime is greater than 20,000 hours. Smaller size per watt of output power is given by CO2 laser. So now let's see about the disadvantages of CO2 laser. The divergence of CO2 lasers approximately in all cases is greater than H-neon and argon laser. Usually the divergence is in the range of 1 to 10 milliradians. Beam width varies from 3 millimeter to 100 millimeter. Some CO2 lasers have the disadvantage of a shorter and thick optical cavity. Cooling system requirement in some configurations also a disadvantage. Its cost is comparatively high. In TEA design of CO2 laser, it is very difficult to maintain ionization in the gas. So now let's see about the Nd:YAG laser. The laser having the solid material as an active medium is called the solid state laser. There are two classes of solid state lasers, continuous wave types and pulsed solid state lasers. The output characteristics of the two are different, while the construction and function of all solid lasers is same. So the Nd:YAG, which stands for neodymium doped yttrium aluminium garnet, is a crystal that is used as a lasing medium for solid state laser. The dopant triply ionized neodymium Nd3 plus typically replaces a small fraction, 1% of the yttrium ions in the host crystal structure of the yttrium aluminium garnet, since the two ions are of similar size. It is neodymium ion which provides the lasing activity in the crystal. So let's see about the characteristics of solid state laser. First we'll see about the continuous wave type. The term continuous wave normally indicates that a laser has continuous output. Usually in CW case of laser is continuously pumped. There are few solid state crystals that can produce laser light and resist the extreme heat generated by a continuous wave pumping source. Only common laser of this type is the Nd:YAG. Output wave of the Nd:YAG laser is 1.064 microns, which is the near infrared spectrum. The beam diameter varies from 0.75 millimeter to 6 millimeter, while beam profile can be either TEM or multimode. The TEM beams tend to have narrower beam diameters. Importantly, note that the beam divergence from a solid state laser is not constant. As the laser rod gets heated by the light source during pumping, thermal expansion occurs. So when the rod gets hotter, the rod expands even more, so causing greater divergence. The beam divergence of CW solid state laser can be as low as 1 milliradian for TEM mode laser, or as high as 20 milliradians for multimode lasers. The output power for the CW solid state laser varies from low of 0.4 watt to a high of 600 watts. Since a Q switch can be inserted between the laser mirrors, therefore a very rapidly pulsed output can be obtained. In addition, the CW pumped solid state lasers can be mode locked for the production of ultra short pulses. In fact, these lasers can produce a CW modulated, CW Q switch or mode locked output. So now let's see about the pulsed type. The pulsed solid state lasers produce a pulsed output due to the pulsing of the input energy. In pulsed laser, the material used can be cooled between pulses. Therefore, the active medium does not exposed to the extreme temperature rise experimental by a CW laser. That is why there are more choices of active medium for pulsed laser rather than for CW solid state lasers. When Nd:YAG is used as active medium, then it can be pulsed very rapidly because it can even withstand the extreme thermal loads of CW operation. So the Nd:YAG lasers typically emit light with a wavelength of 1064 nanometer in the infrared. However, there are also transition near 940, 1120, 1320 and 1440 nanometer. It is very common to pulse YAG laser a rate of up to 200 pulses per second. However, if ruby or ND glass is used as active medium, then pulse rates are limited to 2 to 3 pulses per second. The additional time between pulses is needed to cool the crystal to prevent fracturing. Beam diameter of pulsed laser is in 5 to 10 millimeter range. Beam divergence ranges from 1 milliradian to 10 milliradian. Power output from pulsed laser averages from 400 watts, although the peak power of individual pulses is much higher. So the construction of the solid state laser, here we can see the reflector and pumping cavity, the pump lamp. So usually all solid state lasers have similar design. A laser rod is mounted near an arc or flash lamp. The lamp is connected to a DC power supply that maintains a controlled current through the lamp. The laser rod and lamp are placed parallel to each other and are surrounded by a reflector. The high reflector mirror and the output coupler are placed at either ends of the laser cavity. For simplicity, we do not show the DC power supply and cooling system. However, they exist in solid state laser. So, functions of a solid state laser. We know that active medium used for solid state laser is solid material. Usually, all solid state lasers are pumped optically, means light source is used as energy source of the solid state lasers. When a solid material rod absorbs the light energy from light source, then becomes excited. The upper energy level of the ions or radiation less. However, when the energy transition takes place, then the metastable upper laser level is soon reached. At this point, the emission occurs, which obviously results in lasing. So here we can see the radiation less transmission and also the lasing transition within a wavelength of 1.06 microns. So the application of solid state laser. So NdX solid state lasers are usually used when drilling holes in metals. They are also used in medical applications such as in endoscopy, and in military application it is used as a target destination system. So the advantages of solid state lasers. No chance of wasting material in the active medium because your material used is in the solid form and not in the gas form where this occurs. Both continuous and pulsed output is possible from solid state laser. Solid state lasers have high efficiency compared to some of the gas lasers such as helium neon lasers and argon laser. Efficiency of solid state Nd:YAG laser is 2 to 3%. Construction of a solid state laser is comparatively simple. Beam diameter of the solid state laser is very less than CO2 lasers. Output power ranging from very low value of about 0.04 watts to high value of about 600 watts. The cost of solid state lasers is economical. So disadvantages of a solid state laser. Efficiency of solid state laser is very low as compared to CO2 laser. Great disadvantage of a solid state laser is the divergence, which is not constant and ranges 1 milliradian to 20 milliradian. Output power is also not very high as in CO2 lasers. Due to thermal lasing in solid state lasers, the power loss occurs when the rod gets too hot. So the producing of a solid state rods for lasers is that the active medium in solid state laser can be one of the different crystal. These crystals are not found in nature, but rather they are produced commercially, such as ruby, Nd:YAG, ND glass, herbium, etc. The crystals used in laser are made by doping a highly transparent host material with a metal that will lace. For example, YAG material that has been heated and is in melted form can be doped with Nd. When a mixture cools, a crystal begins to form. A cylindrical crystal is then carefully drawn from the melted material. When it continues to cool, this process is called growing a crystal. Once the crystal is completely grown, the ends of the cylinder are polished to perfection. The final result is Nd:YAG rod that is used as an active medium in solid state laser. Other solid state laser rods are produced in similar manner. During the above process, that any variation in temperature of the melted material can cause distortion in the crystal. The ND comprises between 0.7 and 1.25 of the total weight of the Nd:YAG active medium. It must be evenly distributed throughout the crystal, or hot spots will appear in crystal. These two can cause distortion. So thank you. This is all about the types of lasers.